Modern science maintains massive libraries of hypothetical compounds. The primary constraint is identifying which candidates justify the immense cost and time required for laboratory testing. Actionable prioritization allows researchers to look past the millions of available options and focus exclusively on the most promising leads. To see how the system makes that selection, we can follow the journey of a single candidate molecule moving through the computational pipeline. While high-resolution 3D modeling is possible, it is often too computationally heavy for massive screening. To maintain a fast and scalable pipeline, the system begins by simplifying these complex geometries. This simplification is achieved through SMILES, a standardized format that translates the molecule's atoms and bonds into a compact string of text. Encoding a physical shape into a sequence of letters creates the essential bridge between chemical reality and the digital processing environment. Getting the molecule into the computer is only the first step. To a standard algorithm, a SMILE string like CCO is a meaningless collection of alphabet letters. The system uses a chemistry toolkit called RDKit to interpret these strings. It serves as the foundational interpreter for the entire pipeline. RDKit parses the text to identify the specific atoms present, mapping how they are connected, and identifying any internal ring structures. It also enforces chemical logic, checking the SMILE string to ensure it represents a molecule that is actually viable according to the rules of valency. Once the string is validated, RDKit provides the actionable chemical context the system needs for its next stage of analysis. This leads to the next hurdle. The machine learning model responsible for the final evaluation cannot read chemical structures. It processes numeric patterns. This diagram illustrates the extraction process. RDKit calculates physical properties like molecular weight and log P. The system then generates Morgan fingerprints, a digital map of binary blocks recording specific structures within the molecule. These physical calculations and structural fingerprints combine to form a complete mathematical profile called a feature vector. The molecule has reached its final digital state, a numeric signature that represents chemistry as pure quantitative data. This numeric profile is fed into the primary decision engine, a machine learning model called a random forest. Unlike a single rigid program, random forest functions like a committee. It uses a collaborative group of independent decision makers to evaluate the data. The model comprises individual decision trees. Each routes numeric features through branches, testing data against learned thresholds. As the pathways converge, after navigating the branches, the trees vote. The forest tallies these individual assessments to reach a combined group decision. By aggregating the votes of hundreds of trees, the system identifies complex correlations that are often difficult for human scientists to spot in raw data. Even with a group vote, a simple positive or negative label is often too broad. Science requires a more precise metric to justify shifting resources to a new candidate. The system applies probability calibration to refine that raw vote, adjusting the model's output to reflect a more realistic confidence level. As the toggle morphs into a dial, instead of a binary label, the calibration provides a granular percentage, such as a 78% likelihood of success, allowing for a much more nuanced evaluation. This percentage allows the candidate molecule to be placed at a specific rank on a prioritized leaderboard. Expansive, as the millions of points stream through the layers. When this scaling logic is applied to millions of candidates simultaneously, the impact of the pipeline becomes clear. Every potential compound is translated, features are extracted, and then evaluated, creating a sorted list that separates promising leads from the surrounding data. By stacking structural translation, feature extraction, and collaborative voting, the system organizes vast chemical libraries into a high-confidence ranking, directing laboratory resources toward the molecules most likely to succeed.